Thank you so much. Hi, everyone. Those intros just make me cringe just a little bit. It's like saying AI, but not. Hi, everyone. My name is Mark. I'm MD at Transmission Co. Tashi has done a fantastic job telling you about the mechanics of optical networking, both in the coherent and pre-coherent days. And just to tie all this together is a small talk I'm doing here to introduce you to what it would be like to build your own optical network. Now, traditionally, this is what an optical network looks like with a service for a customer between two nodes. And you've got a ROADM, you've got amplification, all of these good things that Tashi was speaking about. And if you also joined the workshop yesterday he did with Adtran, they went into this in more detail. But these are the basic building blocks of a WDM network. Now, we are privileged in South Africa that we've got a fairly liberalized fiber infrastructure and provider network. We've got what we'd like to call open access fiber operators that can give you dark fiber at reasonably good commercial rates. DFA, Metro Fiber, Link Africa Liquid, Onitel, Fiber, and so forth. These are some of the people from whom you're able to get fiber within the metro, long haul, regional, etc. And when I say get, I mean, it's dark and it's reasonably priced, which used to be a huge problem for us and in many other countries in Africa where you can't actually get access to dark fiber. And so because you have access to dark fiber, it means you have the opportunity to grow your network beyond just, say, a 10 megabit lease from some provider, for example. Or, you're able to go from wireless to wired if you're doing an FTTH backbone between cell sites and things like this. So between that and where the technology is in the WDM space is we are now democratizing access to optical infrastructure. And that is a huge deal in our industry because a lot of small operators are now able to start accessing 100 gig, 400 gig technology. And it's a lot more difficult to pay for that to a provider who is not yet, at the same mindset as you are. Now, if you happen to be in a market like this where you have access to fiber, you can then begin to play in that space by yourself. So the basic building blocks, obviously, the fiber would be the first one to have, and then the optics. Tashi has spoken about pluggables as well as embeddeds. We'll get into that in a little bit. And then multiplexers, demultiplexers, or the filters. This is where you combine multiple wavelengths into one and place it onto the fiber on the line side to get across to the other end. This is the simplest way you can build a system. When you start getting into a little bit more complexity, you then start to add WDM components like transponders and amplification and ROADMs and all sorts of things. And that complexity also means that while you can increase capacity, you can increase reach, you can increase scalability. It also means you increase lead times because manufacturers have to deliver, and that takes some time. You all know what's going on now with supply chain shortages in the optics space. Some people are behind easily 26, sometimes 48 weeks. So as you go higher up the stack, you do get more capability, but you also get a bit more complexity. Now, on the gray side, which is what most operators of a small to medium scale are used to, 10G, 100G, 1G, 25G, we've got multiple different options that you can look at when you're trying to build your network for the first time. As Tashi has mentioned before, we generally want to refer to the capability of your optical network in power availability or link budget, which is dB. We use kilometers and distance to make life a bit easier so we can understand, which is generally reliable between, say, 1 gig and maybe 100 gig, let's say. But as you go higher up the stack, it starts to matter less what you're looking for from a distance standpoint and matters more what you're looking for from a link budget standpoint. And we measure link budget on the optical space in terms of power, which is dB, decibels. So if you're looking at a fiber, you want to figure out how much loss do you have on that span. And these are rough numbers, which are based on a near-perfect fiber of 0.25 dB per kilometer, let's say. In real life, most fiber is not like this, so your mileage will definitely vary. However, on average, let's say, if you've got a 26 dB loss profile on a link, so let's say between points A and B, you're losing 26 dB of energy, that will get you 80 kilometers at 1G, for example. If you go up to 800G and you're within 7.1 dB on a 0.25 dB per kilometer fiber, you could get about 10 kilometers at 800 gig. So when you're asking your fiber providers for fiber, ask them to give you the OTDR or the fiber loss profile so you can understand how much power you expect to lose between 2 points. And in that way, you plan for how far your fiber or how far the capacity you're trying to raise in the fiber can go. Don't worry so much about the distance, because in real life, the distance really, really only helps if you're below 100 gig. After that, it starts to get a bit tricky. Now, you obviously want to find a way to grow, and the flow of the slides is you're growing incrementally in cost. So one of the cheapest ways to grow into 100 gig capability is with the O-band technology. O-band sits between 1290 and 1325 nanometer. It's a fairly wide band, so you're looking at 200 gigahertz size channels, so you can't have that many, about 8. But the good news is that it allows you to have 100 gig as multiple frequencies. So you can have up to 8 times 100 gig with O-band with a QSFP28 plug form factor. What does that mean? It means that your existing routers that have QSFP28 ports for 100 gig will suffice, because QSFP28 is quite widely available, it's inexpensive, and everybody knows it quite well. You get a reasonable power loss profile, so 18.5 dB roughly will give you anywhere from 30 to 40 kilometers for O-band. The downside with O-band, obviously, is that the pluggable is fixed, it's a fixed wavelength, so you have to match them at either end, which makes sparing a bit difficult. But again, it's a cheaper way to get into multi-channel optical capacity in the gray spectrum. Now, still keeping it passive, you've obviously got CWDM, which we all know is fairly inexpensive. Not that many channels either, about 18, give or take. You also do not need amplification, which keeps your costs down, which is fantastic. And you can actually do as well anywhere from 80 to 120, 130 kilometers unamplified. So again, your costs are coming down, and you're able to do anywhere from 1G up to 100 gig. Okay, so that's coarse wave division multiplexing. It's essentially cost optimized. There's not a lot of capacity, but at least it's a place to start. The next one would also be then passive systems, but now we are moving into the WDM, into the colored space. So passive meaning that you don't have a line system or you don't have any kind of amplification. So with these, we are focusing mostly on the coherent plugs. As Tasha mentioned before, you're moving from NRZ into coherent. And we do that because coherent has a lot of advantages in the DSP, like forward error correction, like dispersion compensation, like preamplification, and things like this. So with coherent, we now have 100 gig all the way to 800 gig, and very soon 1.6 tera. 100 gig coherent will get you about 30 dB, which is, so these are unamplified numbers for those who are interested. So this is before amplification. So you're looking at about 120 clicks, let's say, on great fiber. You're looking at about 20 dB or 80 kilometers for 400 gig ZR. So this is up to 0 dB launch power. If you look at the higher power, which is plus 1 dB launch power, you're looking at what we call the ULH, ultra long haul, or 400 gig ZR plus plus, which is a 27 dB plug. This could easily do 100 and plus kilometer unamplified. And then obviously at 800 gig, this is much more metro, so a slightly lower link budget, but you're able to get 800 gig across, let's say, 60 kilometers, more or less. So this would be ideal for what we'd call the IP over WDM. Even though there's no line system involved, it's still considered IP over WDM because you're running it directly in the router to the other end. The advantage with this, obviously, is you have extremely high capacity over dark fiber. And it's an interesting one because if you look at the price of 100 gig ZR and 400 gig ZR, the cost of the plug is just about the same. So then the question you ask is, if you have this fiber, do you want to light 400 gig or 100 gig? Because the cost is the same. Obviously, the difference is the cost of the router port, because the QSFP28 port is a lot cheaper than the QSFP-DD 400 gig port. But from a capacity standpoint, you now have the opportunity. And if you have access to affordable dark fiber that's reasonably reliable, these are some of the considerations you have to make, because are you going to spend $4,000 on 100 gig or $4,000 on a 400 gig type thing? And yeah, so most of this is compatible with the majority of switch and router vendors, so Juniper, Cisco, Huawei, Nokia, etc. So now we're getting into the previous slide, but now with amplification, so with a line system. And the line system, the distance is obviously going to increase. So as you can see, we've now gone from, let's say, 80 kilometers for the 100 gig all the way up to 300. And 450 for the 400 gig ZR plus, up to 2500 for the ultra long haul, the ZR++, and so on and so forth. So with a line system, you're now able to take that coherent plug, dump it into your router, amplify it with an EDFA or Raman system, and get to the other side. Think Johannesburg, Cape Town. Think Johannesburg, Durban, for example, type thing. And you're running this directly from the router into your line system and out the other side. There is no transponders here. You're not spending any money on expensive transponders, because the majority of the source of revenue for traditional OEMs on the WDM space is the transponders. They cost a lot of money because they embed significantly complex optical engines. So in this case, you're avoiding the cost of transponders. You're still getting the capacity across the distance that you want. So for IP over WDM, the reason it makes a lot of sense, back in 22, the hyperscalers were pushing 400 gig ZR heavily. And for them, it's fantastic because then they remove a lot of components and disaggregate the system. So you go from a traditional system at the top here that you'd see has a standard transponder system and a line system to just having a line system. So you've effectively removed a large portion of the cost of what it takes to build and operate your network, which is the transponder systems, because you're moving all those directly into a plug, into your router or switch. Line systems themselves are reasonably inexpensive and they last a long time. All they do is just amplify spectrum. Doesn't matter what the capacity is. In a bit of a spirit of peering at ZANOG, I put this one together as well just to illustrate to you what you could do with IP over WDM and coherent, building your network. So let's say you have a site, at some other building that is not a neutral data center, and you need to get to, let's say, an exchange point. Could be NAP Africa, could be Inkzade, could be whatever, right? So your router is seated at some device, at some location. Let's say, in this case, I've given an example of a Nokia, and you're trying to get 400 gig across because you're peering at 400G at the exchange point. So on this end, you see you have 300 gig going into the exchange point, and you have 100 gig going to a private peer. This plug could be from supplier A. Doesn't matter who that is. This is, let's say, an Arista exchange point base switch. This router in the middle, which is your peering router sitting at the data center that has the exchange point, this is a Juniper router, MX304, for example. At the bottom, you've got a peering partner who's using a Cisco 9903, 06, can't remember. And then you've obviously got your Nokia device on the other side. So a multi-vendor system, as you can see. And then you've got your coherent plug that's also supplied by vendor Z. Right? So it's a pure IP over WDM play. You've got an IP over WDM system, could be amplified, could not be amplified, doesn't really matter. That talks IP over WDM between the Juniper and the Nokia. This talks 400G gray, could be FR4, could be LR4, to an Arista and to another Cisco. And you have a whole ecosystem here of how this can work for you. Okay, so this is a practical application for peering, but this could be anything. This could be your backbone build. This could be an arrangement you have with another operator, so on and so forth. It's the same thing. In real life, we do have a deployment we did for a customer in Cape Town. This was an amplified system over 130 kilometers between Cape Town and Ezerfontein, which is where we are landing to Africa. And as you can see here, we've got a nice Juniper 7300 router at the bottom, running 2 times 400 gig, a QSFP DD ZR Plus coherent plugs. And these are going straight out of the router into some filters and then into the amplification system. So you've got 2 amplifiers, one east and one west. There's a preamp in there and a booster in there for the distance. Fiber quality was, let's say, average 0.25 to 0.27 dB per kilometer-ish. This is across 130 kilometers. This is carrying 800 gigs, so 400 in each direction. And this is practically what this means in real life. Okay, so as you can see, there's no transponders here, just amplification and coherent plugs. And this is how this customer has built their network. It's not their first network, but this is how they've built their network. It's still cheaper than if they had transponders here. And just to echo what Tashi said before, from a system output, when you look at data, because that's important, this is what it looks like coming out of the Juniper CLI. So all the various optical parameters in there that you can either configure and display are right there as well. So it's easy for you to see. This is based on CMIS. Some vendors might implement it differently, like Tashi said. But if you get a good one that does, you get output like this, and it's quite important also. Now, we then start to get into a little bit more complexity with cost and systems, right? So now we're looking at active systems, also multi-channel, so colored. So you've got 2, and Tashi spoke about this also as well. You've got embedded systems on the left-hand side, which are more traditional. And then now you've got what we call the non-traditional. But in this case, I'll just say pluggable transponders. But these are the new breed of WDM vendors that are coming up right now. And the key differences between them are, obviously, these are embedded, so they're kind of fixed in the hardware. You can't take them apart. You can't disaggregate them, so they come as they are. Whereas on the pluggable side, they're pluggable. So you can remove the plug, use it somewhere else, and bring it back. These are high capacity. Both of them will do high capacity in the metro and core. But what you do get on the embedded traditional ones is that you can have extended reach, like over 2,500 kilometers, because they have proprietary, FEC coding, for example, or proprietary implementations of PCS and other features that allow them to get that kind of capacity reach combination that you don't yet have, let's say, on the other side, but has been coming gradually. So a lot of the proprietary features that you're now seeing on the proprietary side are making it into the pluggable transponder side, but in an open manner. So there'll be a step or 2 behind, but when they come, it will be open, so you can use it between different vendors. So because of that, these are generally used for ultra-long haul, like subsea and things like that. Whereas on this other side, we're looking at national level maybe, like a Joburg, Cape Town as well, something like this in Nairobi, Mombasa, for example. Again, with the proprietary technologies, they can have large, super channels. You're talking 1.6 tera, very soon 2.4 tera, that sort of thing, because those are proprietary systems. But on this other open side, we're now able to do 800 gig super channels. We shall soon be able to do 1.6 tera super channels, I'd say, by the second half of next year. So we're getting there. If you don't need 1.6 tera now, you might not want to spend that kind of money now. So you do have an option. And then again, like Tashi mentioned, a lot of space and power that's eaten up on the traditional side, and much less. This is a half-width 1U system as well. You get the same performance out of it. And then obviously there's a massive cost difference. And because here there's a lot of R&D that goes into this, you're going to be paying quite a lot for licenses, whereas on this side, not so much. Okay. So the concept of the pluggable transponder. Now, hyperscalers generally enjoy IP over WDM because it allows them to disaggregate the network. So on this end, this is how systems have generally been. You've got the optical engine and the optics all embedded in one system, in one line card. And then over the years, we've extracted those two things to the point where now we can have a pluggable transponder where you have the line side as a plug and the client side as a separate plug in the same line card, which is what this is. In this particular instance of a pluggable transponder, all the smarts are in the plug, not in the line card itself. And that presents a massive opportunity for cost saving. Because in a traditional system, you're paying for a lot of R&D for putting an optical engine together. But in this system, you're paying for an open standard, the MSA, Open ROADM, OIF plug that you can buy from pretty much anywhere for a fixed amount. And then the line card itself is just a host, an electrical to optical conversion. That's pretty much it. So while the hyperscalers enjoy IP over WDM, we on the network side are a little bit less adventurous, let's say. We love to see our demarcation points. We love to see our transponders. And we know customer link is here and provider link is there. So we want to see a transponder of some kind. So this is a nice bridge because it does provide the flexibility of the line side through a plug, but it also provides a demarcation on the left-hand side towards the customer without breaking the bank. So you do get the aggregation that you like as a network operator. You do get the demarcation to say, customer, you are there and I am here. And then you also do get the protection as well. So on the pluggable side, the good news is all MSA standardized. So you can buy a plug from any vendor that's supplying a plug. It doesn't have to be from me or from her or from him. It could be anyone that conforms to the standard. And then also because of the size of the transponder, you get a lot of savings in power and space. And generally, it's an overall lower cost. So the pluggable transponder is really an alternative to this other system, which could make for a much cheaper way to introduce WDM into your architecture without you thinking that WDM is no longer accessible unless you have millions of dollars to spend, or rands in this case. And then finally, the infamous single fiber working, single core fiber, whatever you want to call it, is also a very attractive alternative to getting into the space while keeping costs down. In some markets, it is a real thing. East Africa, for example, Kenya, Uganda, Rwanda, Burundi. It's typical to look at single core fiber as an option because the providers do charge for it separately. So you will essentially pay double if you want to have a dual core fiber. So this is a real scenario. Look, generally, if you're looking at extremely low capacity, it's fine. But, I mean, I won't go through all this on the right-hand side. You can see for yourself. It doesn't scale well. So if you're trying to get beyond, let's say, 100 gig, couple of 100 gig channels, 400 gig and above, you will start to hit limitations because you're putting a lot more energy into a single core fiber. So there's a lot more you can't get out of it. Just like Tashi said, everything's a trade-off. You get some, you lose some. So you put that much energy into one single core fiber, you won't get that much out of it. By splitting it between two core fibers for a pair, one transmit, one receive, you have a lot more room to grow. So these are all the limitations. So as you can see, there's only really two real benefits, which is, lower cost, but you have a limitation of capacity. You have a limitation of reach. You have a limitation of management. You have much more expensive optics because the precision with single core is much more demanding, and so on and so forth. So I would say if you're trying to maybe stick below 40 gig, 100 gig, maybe one or two channels, fine. But if you're looking at several 100 gig channels, you're looking at several 400 gig channels, and most especially if your fiber providers doesn't make a difference in costs between single and dual, just go dual day one. You have many more options in the vendor space for dual core fiber than for single core. So I'd say unless your market is doing a single core fiber thing, just don't do it. Thank you.
Do we have any questions? We still have about 5 minutes available, so no? So there's one. Oh, okay, you can come to the microphone, please.
Hi, Jessica. So my question is, what would be the imperative of building your own optical network if we are already in a world where we have enough peers, providers, partners, etc., that you could leverage services from and then have the risk sort of removed from your books? Thanks.
Yeah, thanks. So, I mean, the incentive obviously is for you to grow as exponentially as you can for the lowest cost possible. I mean, you could obviously get a terabit of services from another provider, but it's going to cost you $1 billion, let's say, to be a bit facetious. Yeah, so it's really just to lower your operating costs. That's pretty much it. And you do get your network growth to a point where it stops to make sense to pay a third party for the privilege. Okay, so, I mean, think about it, right? Like, when Google started, they probably had, I don't know, a couple hundred gig, let's say, right? Now they're pushing petabytes of data. Even if they got a service for $0.00001 per meg, it will still be too costly for them. So your network does scale to a point where it makes more sense to buy dark fiber from somebody else and then leverage that for as much capacity as you need. And we'll all get to that point as our networks grow. Obviously, before you get to that point, it does make sense to invest in a third party because they've built that infrastructure and they can de-risk that for you. But as you get to that point, it doesn't make sense anymore. Like if you're a typical network trying to push terabits of capacity, you're going to be hard-pressed to find anyone that can give it to you even as close to zero as possible without being too expensive. Make sense? Okay. Thank you very much.
Thank you, Mark. So you get this. Thank you. So this concludes our session. So there is lunch now, which will be until 2:30. So if you want to